My name is Chuanbo. I'm a senior energy storage engineer in the Electrochemical Energy Group at the National Renewable Energy Lab located at Golden, Colorado. My talk today focuses on fast charging of lithium battery to accelerate the adoption of battery electrical vehicles and transportation decarbonization. Fast charge is becoming an essential feature for battery electrical vehicles. It's expected battery electrical vehicles can be recharged within a similar amount of time as refilling conventional gasoline vehicles. While there are fast charge cells available, they are cost prohibitive or have poor life. For transportation application, it requires high energy density lithium battery with fast charging capability. In the presentation, I will overview the transport and damage limits of fast charging, especially lead plating. Physical-based model has been used to develop fast charging strategies. Among them, I will focus on temperature. Currently, vehicle OEMs are using both small cells like Tesla and Rivian and large cells like BMW. For large size cells, thermal management requirements need to be re-evaluated for fast charging. At the last, I will introduce the advanced engineering solution we are developed with AllCell technology. Related to the battery design and material, there are battery, energy battery, and power battery. Power battery has thin electrode, low energy density, and it can be fast charged. Energy cell has zinc electrode, high energy, and must be slowly charged. There are several limits and consequences for fast charge of energy cells. First one, electrolyte gradient. Large concentration and percentage gradient in electrolyte phase to support high current result in non-uniform utilization of media zinc electrode. In extreme cases, electrolyte concentration approaches to zero. Shut off an electrode utilization near current collector. This may result in lead plating particle cracking near separator. Second, saturation at graphite surface. Lithium concentration at solid surface approaching its maximum at the surface of graphite particle, as well as excessive potential gradient and slowed kinetics, which can cause lead plating. And also depletion at anode surface, cathode surface, such like NMC surface. The lithium concentration approach to zero causes material instability, resulting in cathode cracking. The U.S. Department of Energy aims to achieve a charging goal with 3 miles range on a single charge and 15 minutes or less charging time by 2025. This requires high energy density lithium battery with fast charging capabilities. Lead plating is a formation of metallic lithium around the anode of a lithium battery during charging. It causes lithium battery to fail over time. Lead plating is associated with heterogeneity. Heterogeneity leads to inhomogeneous distribution of lithium, resulting in stress that may cause lead plating. Lead plating can occur at wide scales from micrometer particle up to the meter cell. Some heterogeneity is a bulk response, such as electrolyte, uh, due to its transport limitation. Some heterogeneity can be manageable, such as pressure, temperature, and tab configuration at the cell level. In DOE Extreme Fast Charging Program, a combination of cell testing and electrochemical thermal modeling is used to investigate the fast charging performance of cell with a low loading of 1.5 milliampere hour per meter square and moderate loading at 2.5 milliampere hour per meter square. Cell with low loading withstanding extreme fast charging performance remarkably well, even up to non-C, constant current charging with high charge capacity, high Coulombic efficiency, and very little lip plating. For moderate loading cell, the 6C CC charge capacity is poor, with significant amount of observed lip plating. The electrochemical model has been used as feedback to experiments and provide guidance on cell designs and requirements to improve fast charging acceptance at 6C to at 4C to 6C CC charging, and surprise depleting for cells incorporating loading beyond 3 milliampere hour per meter square. The electrochemical model has been validated for low loading and moderate loading cells. Based on all experimental data, prediction of fast charging limitations such as electrolyte depletion, onset of lip plating are reasonable. Model also compared with the recent 1C rate operando XRD measurement from Argonne National Lab. To further investigate the nature of the difference in charging behavior between the low and moderate loading cell, the overpotential at the end of constant current charging was characterized by current interruption voltage relaxation. This analysis is focused on distinguishing between overpotential associated with almost instantaneous phenomena impedance and that has a characteristic time transport. While lip plating occurs, the moderate loading cell exhibit a transport over potential plateau at a rate above 4C, indicating the high rate charging acceptance is severely limited by transport losses. The electrochemical model fits the measured over potential well and is used to investigate the cause of the severe transportation limitation measured for moderate loading cell at high charging rate. Extreme electrolyte concentration resulting in very sluggish lithium transport and poor electrode utilization. For low loading cell, this is enough electrolyte diffusion to prevent electrolyte depletion in the anode phase even at non-C. However, for the moderate loading cell, electrolyte depletion within the anode and high salt concentration within the cathode occurs for charging rate higher than 4C. Thus, at rates higher than 4C, insufficient electrolyte transport resulting in severe transport losses and non-uniform electrode utilization for moderate loading cells. To meet specific volumetric energy density and cost requirement, EV cells must have a sufficient high loading of 1 to 5 milliampere hour per meter square. The electrochemical model is used to investigate various approaches to enable extreme fast charging without lip plating for cells with a loading of 3 and 4 milliampere hour per meter square. This figure illustrates model prediction for achievable energy density during 4C and 6C charging to 4.1 volts for cells with a loading of 3 milliampere hour per meter square. The white section of bars represents where model predict lip plating will occur. Elevated temperature reduced reducing electrolyte tolerability and improving electrolyte transportation are to be suitable strategies worth pursuing. Increase the NP ratio is shown to be ineffective, and the increased porosity is only marginally effective due to loss of overall energy density. For a loading of 3 milliamp hour per meter square, combination of operating of 45 degrees Celsius with electrolyte having reduced the theoretically unable and energy density of 186 and 104 watt-hour per kilogram during 4C and 6C cc constant current charge, and it can be a viable near-term technology. It's also important to continue research on next generation electrolyte. Next generation electrolyte with 1.8 ionic conductivity, 3 times diffusivity, and increased transference number are predicted to enable good extreme fast charging performance for high loading cells. To further investigate extreme fast charging enhancement from temperature, moderate loading cell was charged at 6C for a total charging time of 10 minutes at 20 to 50 degrees Celsius, and the results are shown as dashed line in the top figure. After 10 minutes charge, cells was discharged at silver 2. Each cell was cycled 5 times at one temperature and then cut open in discharge state to visually inspect for lead plating. Thus, each charge curve at a different temperature is from a different cell. The final SOC achieved after CC and CV was 16, 36, 38, and 52% SOC. Thus, increasing operating temperature significantly improve high rate charging acceptance. Bottom figure illustrates picture taken of the graphite anode in discharge state after cycling at a different temperature. Large amount lithium shining silver area here are seen for the cells open at 20 and 30 degrees Celsius. Conversely, very little lead plating is detected for cells opened at 40 and 50 degrees Celsius. Similar result can be realized for 4 milliamp hour per meter square and non-conventional electrodes, but the operating temperature must reach to 60 degrees Celsius. 60 degrees Celsius would require development of suitable coating electrolyte additives. Again, it's important to continue research on electrolyte with enhanced transport. 2 times ionic conductivity, 4 times diffusivity, and the transference number increase by 0.15 is ideal. Except improvement charge acceptance and lead plating, elevated temperature will significantly impact battery life. To address this, physics-based surrogate life model of high quality, long calendar life commercial NMC graphite cell was used to analyze life benefit detriments of elevated temperature fast charging. This commercial cell has a low calendar fade. Cells survive 1 year at 90% SOC at 60 degrees Celsius. Testing data include silver 3 and 1C charge rate. We also include cathode cracking mechanism, Arrhenius temperature dependence without considering lead plating mechanism. As such, this 6C charge rate is a gross extrapolation, but it's still illustrative. We picked a agent profile like this. First, heating up the cell to 60 degrees Celsius at within 30 seconds. And then after the charging, after 60 charging, there is a 10 minutes rest. Then with a 1C discharge. And then we cool down the cell with different cooling constant. We picked 10 minutes and 60 minutes respectively. Cooling time constant is the time to draw down cell temperature by 65%. For this long candle life battery, during accelerate cycle life testing, 10 minutes cooldown has slightly life benefit versus 60 minutes cooldown. At 20% capacity feed, rapid cooldown has about 7% longer life. If we consider the real case scenario, for example, have 1,000 fast charging occurred over 10 years, 20% longer battery life can be achieved with rapid 10 minutes cooldown. This will reduce if fast charge more often, such as 1,000 cycles over 3 years. The benefit will be 17 longer life and 1.5% more capacity. Trade-off is the cost of a large battery thermal management system versus 2.5 larger battery to account for extra feed. Other scenarios which addressed are fast charging temperature and fast charging. The model estimated 150% longer cycle life when 6C charging at 60 degrees Celsius compared to fast charging at 35 degrees Celsius. It's worth to mention the model accounts for cathode cracking and SEI growth, no lip plating. Lip plating will also see benefits. As mentioned before, lip plating can be provoked with heterogeneity. Heterogeneous behaviors become significant for large cells. The 3D model captures the heterogeneity caused by non-uniform. This 3D model captures the heterogeneity caused by non-uniform electrical and thermal field within a 3-parallel 2-series module. Cooling with a liquid-cooled cold plate. It was found that electrode close to the tap was preferentially used during charge. The heterogeneous behavior was increased as the charge rate increased. Simulation results suggest two related reasons to generate heterogeneity. One is the higher voltage of sandwich electrode close to the tap, and a higher temperature of electrode away from the cold plates, leading to lower resistance of electrode. Cell electrochemical heterogeneity can be reduced by decreasing cell temperature difference. This can be achieved by enhancing cell thermal conductivity and arranging heat transfer pathway more evenly, such as doubling thermal conductivity of the cell and using fins on both sides of the cell. Additionally, optimal design of the cooling surface to the cell is necessary. For the same cold plate modeling scenario, we continue to use this module and investigate cooling on multi-surface. The heat generated by the cell was shunted to multiple cooling plate design. During this study, we found the significant heterogeneity mitigation was achieved by cooling the cell on multiple sides as shown. The cooling power for each simulation was held constant, except for the constant inlet temperature case, which assumed the inlet temperature was maintained at 30 degrees Celsius. Compared with bottom cooling, bottom and top cooling reduced temperature and the DOD difference within the module by about 10 degrees Celsius and 4% respectively at the end of 6C fast charging. With additional type cooling, the DOD difference was further reduced by 3%. Supported by our RPE program, our group worked with industry and university partners to develop an active cell electrical management system enabling cell differential control of strong versus weak cells. 12-volt loads is used to differentially balance battery cells. Low-cost isolated bypass DC-DC converter modules connect each cell to the vehicle 20-volt bus pass. Existing DC-DC and battery management system is replaced with integrated modular BMS DC-DC. Life balance lead to reduced capacity imbalance that can be caused by factors such as pack temperature gradient and slight manufacturing variance among cells, increased lifetime, and relaxed thermal management. Range is no longer limited by the weaker cell in the pack. Proposed system architecture and life balancing was experimentally validated. For fast charging application, it's expected the life balancing will be more beneficial. Support by Shell Game Changer program powered by NRAR. We have been working with AllCell to develop and validate a battery pack prototype integrated with AllCell's integrated battery thermal management technology for fast charge application. AllCell technology designs and manufactures lithium battery packs for portable, stationary, um, and transportation applications. AllCell's passive thermal management technology is based on the use of phase change composite, short in PCC, a mixture of white and porous graphite matrix to surround each lithium battery cell, absorbing and conducting heat away to extend the life of the cells and prevent fire or damage to the battery. A well-designed thermal management system is critical to battery performance and life. Development of precisely calibrated thermal management system relies on accurate characterization of battery electrical and thermal behaviors. A working prototype for fast charge should effectively control the cell temperature and minimize temperature non-uniformity. To achieve this, NRAR's isothermal battery parameter was used to determine the heat level and energy efficiency of a nickel-rich NMC cell. Except the C-rate, there are some charging parameters evaluated, such as charging voltage windows and expected capacity. Also, a two-resistor capacitor equivalent circuit model is then developed and validated. The model works for both load cycles and constant rate loadings, providing enough accuracy in estimating not only battery electrical response, but thermal response. This result has been used for PCC design, optimization at AllCell. The prototype design here is an optimized outcome. Compared with Pack 1, the weight of the PCC housing case of Pack 2 is reduced by 10%, and the cell was relocated. Simulation result shows at 2C charged to 50% SOC. The Pack 2 can maintain minimum temperature difference among the cell, as can be seen from this figure. To compare long-term battery use strategies, battery lifetime analysis is crucial. This was achieved with NRAR's lifetime model. This model is a predictive model extending expensive lab battery agent dataset to real-world scenario. The model's trial functions are statically regressed to lithium life data sets where cells are aged under various conditions. Using this statistical framework, degradation mechanism Along with temperature and the cycling factor, are regressed to produce a lifetime prognostic model. By analyzing agent data from AllCell, 3 scenarios was identified, including calendar fade, moderate normal cycling, and fast charging cycling. The criteria to distinguish moderate um, cycling and fast charge cycling is not only related to charging rate, but temperatures. For example, moderate charging rates are defined less than 1 C at 25 degrees Celsius, and it will be less than 1.5 C at 35 and 45 degrees Celsius. This is related to the concentration gradient in active material particles, calculated by charging and discharging rate times square root of charging discharge time. The middle figure shows the rate of capacity loss per cycle as a function of concentration gradient, captured by a sigmoidal function around concentration gradient 1. Sudden damage occurs, and the rate of capacity loss significantly increased, as can be compared by the uh, testing condition in the red box. Fast charging at 25 and 35 degrees Celsius, the loss rate was similar. At 45 degrees Celsius, lower rate of fade can be achieved. Model regression indicates capacity fade at fast charging cycling is caused by lithium site loss. At moderate cycling, capacity fade was mainly due to lithium inventory loss. Considering temperature management is required for fast charging, a technology expanding on the current use of phase change composite technology is proposed by AllCell. This is done by using phase change material, incorporate between individual cells as the resistive heater. This proposed technology will enable direct rapid heating of the individual cell due to the pre-existing phase change composite lithium cell integration and the thermal transfer concept already established without impact on energy density and cost from an increase in non-battery preheating components. The phase change composite will need to be designed to enable rapid preheating while still maintain substantial thermal conductivity and latent heat characteristics for passive thermal management performance. Proof of concept for preheating was carried out with 3D phenomenon element analysis of PCC stream. The result demonstrated nearly 10 degrees Celsius increase can be achieved in about 10 minutes with PCC phase change composite heating. A prototype experiment is in progress. Besides study at room temperature and beyond, we have been working with AllCell to broaden this technology for fast charging at sub-zero temperatures. The first goal is to develop a baseline fast charging at varying ambient temperature. Left figure shows the charge acceptance as function of charging C rate and ambient initial temperatures. In general, charge acceptance become worse with higher C rate and lower temperature. At 0 degrees Celsius, the charge acceptance is 50% with a 2C rate, indicating cell can be charged to 50% in about 15 minutes. However, charge becomes unacceptable with 2C rate at minus 20 degrees Celsius. To charge the cell at minus 20 degrees Celsius, effective preconditioning by warming up the cell is necessary. It's worth to point out that self-heating is should be considered to work with warm-up technology. The developed Development of fast charging capable lithium battery pack is a system-level concern. All parts in the system, including lithium battery cell, battery pack, battery management system, and any thermal management system, need to be optimized and carefully integrated. This flowchart representatively illustrates an integrated battery thermal management framework to analyze, control, and optimize fast charging uh, capable lithium battery pack. The temperature of the battery pack will be increased before the charging step to improve the electrochemical kinetics while charging. The temperature will be limited by choosing the suitable wax or other phase change material with a desired phase change temperature. The integrated battery thermal management system would also be able to communicate with the charger based on the electrical and thermal status of the battery pack. Input to this battery charging algorithm will be cell and phase change material temperature, a state of charge, state of health, voltage, and current in an integrated manufacturing feedback loop. And that brings me to the end of my presentation. Let me give you a summary of what I have been talking about over the last half hour. First, we talk about the fast charge is limited by transport and damage, especially for high energy density cell. Ideally, next generation electrolyte with higher conductivity and diffusivity will be available. A combination of solution, however, is practical as a near-term technology. Among the strategies we evaluate, temperature control is important for fast charging. Effective method should uh, Effective thermal management method should warm up and cool down battery efficiently. At system level, minimize temperature heterogeneity is vital. Life-driven life balancing may become necessary. Recently, we worked with AllCell to develop a thermal management solution based on phase change composite. It's promising this technology will work for both normal temperature and sub-zero temperatures. Thank you.